You're about to learn about OpenGL from Victor Gordon. He has created an excellent course for beginners, with simple-to-follow instructions and informative diagrams.
Welcome to this beginner's course on OpenGL. If you're wondering what OpenGL is, well, it's a cross-platform graphics API that allows you to render 3D and 2D scenes with the power of your graphics card. Usually when programming, we use our CPUs, which are great at doing a huge variety of tasks one after another in a linear fashion. But when we deal with graphics, a lot of the tasks are very similar and don't usually depend on one another, so the fastest way to get a result would be by doing all of them at the same time in parallel. This is what GPUs, or graphics cards, excel at. OpenGL is simply a way for us to communicate with the GPU. By the end of this course, you'll be able to import basic 3D models such as these into your application and have a firm grip on the basic concepts of computer graphics. Everything from basic buffers used to send data to the GPU to classic lighting algorithms and shaders. The only things you should be familiar with before we start are the basics of the C++ programming language and the basics of Visual Studio, since that's the IDE we'll be working with. The first thing you'll want to do is to check you have the latest drivers for your graphics card and the latest version of Visual Studio. Next, make sure you download the 64-bit Windows installer for CMake and go ahead with the installation. Now download the source package for GLFW. Lastly, you need to download GLAD. Make sure you select C/C++, version 3.3, core, ignore everything else and press the generate button. Now press on the glad.zip to download it. Once you've finished installing CMake and Visual Studio, open up Visual Studio and click on Create New Project. Select Empty Project for C++, click Next, type in a name for your project, make sure the checkbox is checked, and remember in what folder you've placed your project. Open up the folder of your project and create a new folder, naming it Libraries. Now we'll create another two folders in Libraries, naming them Lib and Include. This is where we'll later import all our libraries into. Now we need to extract the GLFW zip file and open up CMake. In CMake, select the folder we've just extracted as the source folder. Then create a new folder named Build in the source folder and select it as the build folder. Now click on Configure, and after making sure you have the same settings as me, click Finish. Now again, make sure you have the same configuration as me and click on Configure again. Click on Generate, and once everything is done, exit from CMake. Now we want to build GLFW, so open up the folder you've extracted, then build, then open up glfw.sln in Visual Studio. Right-click here and select Build Solution. If this gives you any errors, it probably means that you've messed around with the build, and we'll thus have to regenerate GLFW using CMake and follow this step again. Once your build finished successfully, exit from Visual Studio. Now it's finally time to import our libraries in. So open up the GLFW extracted folder and go into Build, Source, then Debug, and I'll cut and paste glf3.lib into your lib folder that's inside your libraries folder. Back to the extracted GLFW folder, go into Include, cutting and pasting GLFW into the Include folder of your project. Assuming you followed the steps correctly, you can now delete the extracted GLFW folder and open up glad.zip. Open up Include and extract the two folders into your project's Include folder. Now go a folder back and open up Source, extracting glad.c into your project's Main folder. We'll now configure our Visual Studio project to know where to access the libraries from. So open up your project and make sure you have 64-bit selected. Now go to Project, Properties, and select all platforms for your platform. Then go to VC++ directories. Open up Include Directories and point to the Include folder in your Libraries folder. Click OK, and now do the same for your library directories with your lib folder. Once you're done with that, go to Linker, Input, and open up additional dependencies. Here we'll write glfw3.lib and OpenGL32.lib. Don't worry, even though it's called OpenGL32, it's still the 64-bit version, it's just a naming convention. Now click OK and OK. The last thing you have to do is to drag the glad.c file from your project folder into your source files folder in Visual Studio. Then right-click Source Files, click Add, New Item, select C++ file, name it Main.cpp, and click on Add. Now, in order to test that everything is fine, include these and type int main brackets, curly brackets, return 0, semicolon, and run. If you've done everything correctly, you should get no errors. So now we're going to pick up where we left off and create a window. We're going to use GLFW to do that, so the first thing we need to do is initialize it so we can properly use its functions. And since we've initialized it, we should also terminate it before the function ends. So I'll add this at the end of the function. Now, GLFW doesn't really know what version of OpenGL we're using, so we need to tell it that. We can do that by giving it so-called hints with a special function that takes a type of hint and a value. For example, here I'm giving it a hint that we are going to specify the major version of OpenGL that we are using, and then I give it the version itself, which is 3, since we are using OpenGL 3.3. Now I'm just going to do the same for the minor version, which is the exact same one. The last hint we have to give it is about which OpenGL profile we want to use. So I'll type glfw_OpenGL_profile. Now, an OpenGL profile is sort of like a package of functions. As far as I know, there are only 2 packages. Core, which contains all the modern functions, and compatibility, which contains both the modern and outdated functions. We only care about the modern ones, so I'm going to use the core profile. Now for the window itself. This is the data type of a window object in GLFW. Let's just name it window and use the create a window function. This will take 5 inputs: the width of the window, the height of the window, the name of the window, whether we want it full screen or not, which we do not, and the last thing is not important. And just to be on the safe side, I'll add a bit of error checking in the case in which the window fails to create. So great, we now have a window object. Problem is, GLFW isn't the brightest kid around the block. So I'll now have to tell him that since we've created the window, we would also like to use it. Who would have thought? This tells GLFW to make the window part of the current context. A context being a sort of object that holds the whole of OpenGL. It's a bit abstract, as context can hold and do many things, but we'll just go with this for now. Now, just like before, once we are done with the window itself, we want to delete it. So let's do that at the end of the main function. If you run the program now, you'll maybe be able to spot a window pop up and instantly disappear into oblivion. That happens because once the main function finishes creating the window, it just continues to go about its business and tries to reach the end of itself, which when it does, it ends the whole program. In order to stop that from happening, we need to make a while loop, which will only end on the condition that the window should close. That condition will only happen when we press the close button, or if another function tells the window to close. And now, just one more thing before we get our glorious window. We need to tell GLFW to process all the pulled events, such as the window appearing, being resized, and other such things. If we don't process those events, the window will just be in a state of not responding. And now, press run and watch the fruits of your labor. But I find this white window kind of boring, so let's add some color to it. We'll start doing that by finally using GLAD and telling him to load the needed configurations for OpenGL. Then we'll tell OpenGL the viewport of our window, which is just the area of the window we want OpenGL to render in. That will go from the bottom left corner of the window, coordinates 0, 0, to the top right corner of the window, coordinates 800, 800 in our case. Now, in order to go forward, I'll have to introduce some computer graphics concepts. So, lesson time! Yay! As you probably already know, screens display a bunch of images really fast, which give us the illusion of motion. These images are called frames. Screens display frames by changing from the pixels of the display to the pixels of a frame. These are changed one by one from the top left of the screen to the bottom right of the screen. Now, while the screen is loading the pixels from the current frame and displaying them, the next frame is being written in the background, away from our eyes. Once the screen finishes displaying the current frame, it switches it with the next frame and starts displaying that, while in the background, the now previous frame is being overwritten with new information. These two frames are called buffers, and they're simply a space of storage in memory for pixels. The buffer from which information is being read to be displayed on the screen is called the front buffer, while the other one, on which information is being written, is called the back buffer. Now let's write the actual code. We're going to tell OpenGL to prepare to clear the color of a buffer and give it another color. I'm going to give it a nice navy blue in the normalized decimal RGB form of color, and set the last number, the alpha, to 1. The alpha number dictates the transparency of the color, 1 being opaque and 0 being completely transparent. Now we want OpenGL to execute the command we've told it to prepare for. So we'll use this function specifying we want to use the command on the color buffer. We'll learn more about types of buffers in the next video. So at this point, we have a back buffer with the color we want, and the front buffer with the default color. So in order to see our color, we'll want to swap the buffers, since only the pixels on the front buffer are being displayed. Now, press run, and ta-da! We now have a nicely colored window that you can show off to your imaginary friends. And the last thing that's left to do is just to write some comments so that you can make sure you understand what's happening. Try writing them with your own words, but if you find that difficult, then feel free to copy mine. I'll leave the source code in the description and the PDF with some exercises so you can practice what you've just learned. So now let's add a triangle to the mix. But first, I'll have to introduce you to something called the graphics pipeline. The graphics pipeline is essentially just a series of functions which take some data at the beginning, and then at the very end of the graphics pipeline, it outputs a frame. Now the input is called the vertex data. This is just an array of, well, vertices. Though they're not mathematical vertices, since each vertex, besides having a position, also contains other data, such as color or texture coordinates. The first phase of the graphics pipeline is called the vertex shader. The vertex shader takes the positions of all the vertices and transforms them. Or if you want to, it can keep them the exact same way. Your choice. Once all the transformations are done, the shape assembler takes all the positions and connects them according to a primitive. But what's a primitive, I hear you asking? Well, a primitive is just a shape, such as a triangle or maybe a point or a line. Each primitive interprets the data differently. For a triangle, it would take 3 points and then draw a triangle between them, whereas a line would take 2 points at a time and draw lines between them. Up next, we have the geometry shader, which can add vertices and then create new primitives out of already existing primitives. But this one is a bit more complex, so we won't be seeing it for a long while. Next comes the rasterization phase, where all the perfect mathematical shapes get transformed into actual pixels. So what before was a perfect mathematical triangle now becomes just a bunch of pixels, which are just kind of a bunch of squares. But these pixels don't really have any color to them. So here comes the fragment shader, which is one of the most important shaders. So the fragment shader adds colors to the pixels. These depend on many things, such as the lighting or the textures or shadows. At this point, you might have multiple colors for just one pixel because of multiple objects overlapping. So that's fixed in the last phase, as is the blending of transparent objects into the final color. Now for the actual coding. So sadly, OpenGL doesn't provide us with defaults for the vertex and fragment shaders, so we'll have to write our own. But since this tutorial doesn't focus on the shaders themselves, but rather the overarching process of using the shaders, I'll simply copy-paste the shaders in. Don't worry though, I'll be looking at those in a future tutorial. So first, let's specify the coordinates of our vertices. For now, we're going to work in 2D, so we're going to ignore the z-axis. As for the x and y axis, well, their origin is located in the middle of the window, with x pointing to the right and y pointing up. Now, the coordinate system is normalized, which means that the leftmost part of the window for x is -1 and the rightmost part of the window for x is +1. While for y, the lowermost part of the window is -1 and the uppermost part of the window is +1. So now I'll make an array of data type GLFloat. Why GLFloat? Well, you would probably use normal floats, but these may differ in size from the floats that OpenGL uses, so it's just safer to go with the OpenGL version. There's a link down in the description to a Wikipedia page where you can see all the data types that OpenGL has. Now I'll just name these vertices and add some coordinates. Now in this array, every 3 floats will represent 1 coordinate. I'll first add the coordinate of the left corner, then the right corner, and then the top corner. These may look kind of complicated, but that's because I chose nice coordinates such that I get an equilateral triangle, but you can put any coordinates you want to, as long as they're between -1 and +1. So great, now we have 3 coordinates. So let's just feed them into the graphics pipeline and get a nice triangle. Well, sadly, it's not that easy. We may have the source code for our vertex shader and our fragment shader, but we don't have the shaders themselves. So shaders are an OpenGL object, and these are just kind of like in the background in the memory, and we can only access them by references, aka a value. In fact, all OpenGL objects are accessed by a reference. Keep that in mind, as it is very important. So let's create a value, aka a reference, to store our vertex shader in. So I'll type in GLUINT, which is the OpenGL version of an unsigned integer, aka a positive integer. I'll name it vertex shader and use glCreateShader to create the shader and get the reference value. And as an input, you'll have to specify what kind of shader you want. In this case, we want a vertex shader. So now that we have a vertex shader, let's feed it the source code we copy-pasted earlier. We'll use GL shader source, and the first thing we're going to give it is the reference value. Then we're going to specify that we're only using one string for the whole shader. Then we're going to point to the source code, and then the last thing doesn't matter, just write null. Now the thing is that the GPU can't understand the source code, so we'll have to compile it right now into machine code. So I'll just use GL compile shader and give it the reference value. So great, now we have a vertex shader. So now just do the exact same thing for the fragment shader, only replace everywhere you see vertex with fragment. If you get lost, just check my code. Now, in order to actually use both of these shaders, we'll have to wrap them up into something called a shader program. So just like before, let's create a reference value, name it shader program, and use GL create program. This time not specifying anything else because they're just one type of shader program. And to attach a shader to the shader program, you're going to use GL attach shader, first plugging in the reference to the shader program, then plugging in the reference to the shader itself. Once you've finished attaching your shaders, we want to wrap up the shader program. We're going to use GL link program for that, and we're just going to pass it in the shader program reference. And just to keep it tidy, I'm now going to delete the shaders we've created before because they're already in the program itself. So great, now we're done with the shaders. So you would be tempted to press run, but nothing is going to happen because we haven't done anything with our vertices. We haven't even told OpenGL how to interpret them. So let's do that now. So sending stuff between the CPU and the GPU is kind of slow. So when you do send stuff, you want to send it into big batches. These big batches are called buffers. Do not confuse them with the front and back buffers from the last tutorial though. So let's create a vertex buffer object where we'll store our vertex data. And as always, we're going to use a reference integer for it. Now, the VBO is actually an array of references, but since we only have one object, we only need one. So for now, we're just going to leave it like this. We can create the buffer object by using GL gen buffers and giving it 1 as the first argument because we only have one 3D object, and then pointing it to the reference. Now let me introduce you to the concept of binding. Binding in OpenGL means that we make a certain object the current object. And whenever we fire a function that would modify that type of object, it modifies the current object, aka the binded object. So now we'll just bind it using GL bind buffer and giving it GL array buffer and the reference of the VBO. Now I used GL array buffer because that's the type we need to use for the vertex buffer. If you want to see the other types of buffers, I left a link in the description to the OpenGL documentation where you can look up this function and it will tell you what other kinds of buffers there are. Now let's actually store our vertices in the VBO. We'll do that by using GL buffer data. We first specify the type of buffer, the total size of the data in bytes. We can just use a C++ function to get that. And now we give the actual data itself, so the vertices. And finally, we specify the use of this data. This is done by typing GL underscore, and now we choose between stream, static, and dynamic. Stream means that the vertices will be modified once and used a few times. Static means that the vertices will be modified once and used many times. And dynamic means that the vertices will be modified multiple times and used many times. You need to specify these in order to improve performance. So now we continue with another underscore and again choose between draw, read, and copy. Draw means that the vertices will be modified and be used to draw an image on the screen, and you can imagine what the other two do. So great, now we have a nicely packed object with our vertex data. But OpenGL doesn't know where to even find it. In order to do that, we make use of another object called a vertex array object. This stores pointers to one or more VBOs and tells OpenGL how to interpret them. VAOs exist in order to quickly be able to switch between different VBOs. So let's go back and put VAO in front of VBO. Now let's generate the VAO using GL gen vertex arrays, seeing that we only have one object and pointing to the VAO reference. Make sure you generate the VAO before the VBO. The ordering is very important. Now let's bind the VAO so that we can work with it. Now let's configure it so that OpenGL knows how to read the VBO. We'll do that by using the function glVertex attribute pointer. First, we pass the index of the vertex attribute we want to use. A vertex attribute is a way of communicating with a vertex shader from the outside. I'll talk more about this in the tutorial for shaders. The first input is going to be the position of the vertex attribute, which in our case is 0. The next input is how many values we have per vertex. In our case, that's 3 because we have 3 floats. Next, we're going to tell what kind of values we have. We just have floats. Now, the next input only matters if we have the coordinates as integers, but we don't have that, so just write in gl_false. Now we have to give the stride of our vertices, which is just the amount of data between each vertex. In our case, since we have 3 floats, then that is just 3 times the size of one float. And the last thing is called the offset, which is a pointer to where our vertices begin in the array. But since our vertices begin right at the start of the array, we're going to give this weird pointer void. So finally, we've configured the vertex attribute. Now, in order to use it, we need to enable it using gl enable vertex attribute array and give it 0 because that's the position of our vertex attribute. Now, this next step is not mandatory, but it's nice to have just so you can be 100% sure you won't accidentally change a VBA or VAO with a function. We basically just unbind both the VBO and VOA by binding to 0. Now, once again, make sure you have the same ordering of your functions as I do in the case of the VAO and VBO, because the ordering is extremely important. And just to keep everything nice and clean, let's go to the end of our main function and delete all the objects we've created so far. And now just a few more lines of code and we'll finally have a triangle. First, copy and paste the glClearColor and glClear functions into the while loop. Now let's activate the shader program we've created like 1,000 years ago. And now let's bind the VAO so that we're telling OpenGL that we want to use this one. It's not really necessary to do this because we only have one object and one VAO, but it's good to get used to this. Now for the drawing function itself, we're going to use glDrawArrays, specifying the type of primitive we want to use, triangles in our case, the starting index of the vertices, 0 in our case, and then the amount of vertices we want to draw. Since we're drawing one triangle and a triangle has 3 vertices, that's 3. And last but not least, we make sure we swap the buffers so that the image gets updated each frame. And finally, after a long journey, we can finally press run and see a nice triangle pop up. Now, I can imagine you probably feel a bit overwhelmed by the amount of information you just got. Don't worry though, it's normal. I was also a bit overwhelmed by it at the beginning. So now a good way to make sure you understand most things is to add comments to all the steps and functions and rewatch certain parts that you don't fully understand yet. If you want to know more about individual functions, simply look them up in the documentation of OpenGL. It helps more than you'd expect. So as always, I've left a link in the description to a PDF with exercises for you to do. Exercising and messing around with the functions really helps you learn what each of them does. So now we're going to build on top of that by introducing the concept of index buffers. As you hopefully remember, we can draw a triangle by telling OpenGL to use the triangle primitive between 3 vertices. In this case, vertices 0, 1, and 2. Easy enough, right? But what about this case? Well, here we have 3 triangles, so that means we need 9 vertices: 0, 1, 2, 3, 4, 5, and 6, 7, 8. But as you can probably see, we have duplicate vertices, which means that we're just wasting memory space. So let's rewrite the vertices, but this time without duplicates. So in this case, we have vertices 0, 1, 2, 3, 4, and 5. If we give this to OpenGL, it will draw a small upside down triangle on top of a big triangle, which is not what we want. In order to prevent that, we need to make use of an index buffer. An index buffer tells OpenGL the order in which it should go over vertices. Here, it first goes over 0, 4, 3, then 4, 1, 5, and then 3, 5, 2. We solve the problem of duplicate vertices by simply visiting the same vertices twice using indices. So now let's actually implement this. I'll first add the new vertices to my array. And now I'll create an array of data type GLUINT for the indices and type in the indices we saw previously. Generating the index buffer is very similar to the vertex buffer, so let's first create its reference value. Next, let's generate the reference value and store it in EBO, specifying we only have one object. In order to do something with it, we need to make it current, aka bind it, and also specify it's of type GL element array buffer. Now we link it to our indices array. If you don't know what these inputs mean, check out my previous tutorial. Now we unbind it, but make sure you unbind it after you unbind your VAO, since the EBO is stored in the VAO. So if you unbind it before unbinding the VAO, you're essentially telling OpenGL that you don't want the VAO to use your EBO. And to keep things clean, we'll delete it at the end of the main function. The last step is to replace GLDrawArrays with GLDrawElements, specifying the primitive we want to use, how many indices we want to draw, the data type of our indices, and the index of our indices, which in our case is 0. Now just press run and enjoy your triangles. As always, I've left the source code and some exercises in the description. Now let's organize things a bit, since as you can see, we have a lot of stuff going on in here. Let's start by moving the shaders into their own separate text files. Open up the Solution Explorer and create a folder called Shaders in the Resource Files folder. Now let's add a new item, selecting Utility, then Text File, and naming it default.vert. Open it up and copy-paste the Vertex shader source code into it. Make sure to get rid of the one variable you have and all the quotes and /n's. Now do the exact same thing for the Fragment shader, only name it default.frag instead of default.vert. Now let's create our very own shader class. Go to Header Files, add new item, header file, and name it shaderclass.h. In this file, we'll declare our class and other functions related to it. First, let's write #if and def shader class h, #define shader class h, #and if. This lets C++ know not to open up the file twice, since that would create variable clashes. Now we'll need to declare a function that will read the shader text files. I will not go through the details of it though, since the function itself is irrelevant to OpenGL. Just know it outputs the contents of a text file as a string. Now let's declare the shader class, which will simply be an OpenGL shader program that's nicely wrapped up. Give it a public ID, aka reference, declare a constructor that will take in the shader source codes, and two functions, activate and delete. Once you're done with that, go to source files and create a CPP file named shaderclass.cpp. I'll start by including shaderclass.h and then copy-pasting the file reader function. Link in the description to all the source code. Now let's write the shader constructor. First, let's get the strings from the text files into two variables, and then convert and store them into character arrays. Now we just need to copy-paste all the shader-related code from the main function, modifying it slightly by replacing shader program with ID and changing vertex shader source to vertex source and fragment shader source to fragment source. Don't forget to also write the activate and delete functions by again copy-pasting from the main function. Great, we've made a shader class. Next, let's make a vertex buffer class. Create a header VBO.h and include GLAD for the OpenGL functions. Now create a VBO class, giving it a public ID variable and a constructor that takes some vertices and their size in bytes. The size of the vertices is in the GL size IPTR data type, since that's what OpenGL uses for sizes in bytes. Now just add some declarations for the bind, unbind, and delete functions. Then create a C++ file VBO.cpp and copy-paste the same functions as me, changing the name of some variables such as VBO to ID. Make sure to also copy-paste in the code for the other functions. Now repeat the same procedures we've done with the VBO for the EBO, making sure to replace GL array buffer with GL element array buffer. And now finally, the vertex array class. Create a header and include GLAD like before, but this time also make sure to include VBO.h, as we'll need to link a VBO to the VAO. Create the VAO class, give it a public ID, create a constructor without any inputs, and then a link VBO function that will take a VBO and a layout, which we'll learn more about in the shaders tutorial. Don't forget to declare the usual bind, unbind, and delete functions. Once you're done with that, create the VAO.cpp file and include the VAO header. Now copy-paste in the relevant functions, but make sure to bind and unbind the VBO in the link VBO function. Make sure you've written everything the same way I did. Great, now we're done with creating all the classes. All that's left to do now is to go back to the main function, include all the headers we've created, and replace all the default functions we had with the new functions and classes. I'll also move the vertices and indices to the top of the file, as I think it looks better. If you press run, everything should work just like before. As always, the final step is to add your own comments in order to make sure you understand all of this. If you run into any problems, the source code is in the description. Now let's finally learn more about shaders. You can think of shaders as functions that run on the GPU. Since they're similar to functions, they can take inputs and also have outputs. So let's take a look at our default vertex shader. While looking at this, you might think it's C code, but it's actually OpenGL's shading language, aka GLSL, which has a similar syntax to C. The first line contains the version of GLSL we are using. Since we have OpenGL 3.3, we need to use GLSL 330. The second line takes an input APOS using the layout with location 0. Layouts help OpenGL read the vertex data it receives. In this case, we say that on the 0th layout, there is a vec3 data type for positions. Now for the main function, we simply assign GL position a vec4 with all our positions, plus an arbitrary one for the 4th dimension, which we can ignore for now. OpenGL recognizes the keyword GL position and knows it needs to use it as the position for the vertex. You can think of this shader as outputting GL position, even though it doesn't specifically do that. On the other hand, the Fragment shader specifically says on the second line that it outputs a vec4 color. Now for the main function, we simply gave it a color in RGBA format to use for all the vertices. But instead of having one color for all the points, let's give each vertex its own color. So I'll start by writing RGB values after each position in the vertices array. Then I'll add a second layout with location 1 that takes a vec3 named A color. But since the Fragment shader is the shader that takes care of colors, we need to output the colors from the Vertex shader to the Fragment shader. To do that, I'll output a vec3 named color and in the main function, make it equal to the A color imported from the vertices array. Now in the Fragment shader, I'll input the exact same vec3 named color. It's very important to give inputs and outputs the same name, since otherwise OpenGL wouldn't know to make the link between them in the first place. And the final step for this shader is to make frag color equal to color, since that's what we are outputting. Now we should configure the vertex attribute pointers, but first we need to modify a function from the VAO class. Let's change link VBO to link attrib and add 4 variables: num components, type, stride, and offset. Now do the same in the VAO.cpp file and add in the new variables as inputs to the GL vertex attribute pointer, just like me. So we are sending the shader an array of a bunch of bytes. In order for OpenGL to know how to interpret all of them, we tell it how to do so in the GL vertex attribute pointer function. First, we specify the layout location. In our case, 0 for coordinates, /position, and 1 for color. Then the number of components per layout, 3 in both of our cases. Then the type of our components, GL float, and finally the stride and offset. The stride is the distance in bytes between the beginning of one vertex and the end of another, which in our case is 6 times the size of a float, since each vertex has 6 floats. The offset is simply the initial offset of a layout in bytes. For the coordinates, that's 0 because they are right at the beginning, while for the colors, the offset is 3 times the size of a float in bytes, since the first 3 components are coordinates. Now let's write all of this in code by linking the attribute for coordinates and colors from our VBO to our VAO. Now if you press run, you should see that the triangles have a nice gradient of color. You might be asking yourself why there is a gradient of colors even though we only specified a couple of colors. Well, that's because if a primitive has different colors for its vertices, then OpenGL will automatically create a nice gradient from one color to another. This is called interpolation, and it is used in other things besides colors as well. Now let's look at the second method of getting inputs and outputs within and outside of a shader. This second method makes use of uniforms. Uniforms are sort of like universal variables that can be accessed by other shaders and can even be accessed from within the main function of the program without the use of a VAO. Let's create a float uniform called scale in our vertex shader. Now let's just add to each coordinate the corresponding coordinate multiplied by the scale. What this essentially does is it increases the size of our triangles. So if the scale is, let's say, 0.5, then our triangles are 50% bigger. One thing to note though is that you should never declare uniforms if you're not going to use them, since otherwise OpenGL will delete them automatically and that may cause errors. Okay, now in order to give the uniform a value, we must first get its reference value in the main function. We'll do that by using glGetUniformLocation and store the reference in an OpenGL unsigned integer variable called UniID. The function will take as inputs the reference of the shader program and the name of the uniform. Now, in order to give it a value, we must use the glUniform function, but we can only do so after activating our shader program, so make sure you write it after shaderprogram.activate. glUniform is a bit of a weird function, as its name's suffix changes depending on the data type we are inputting. If you want to know all the variants of the function, look it up in the documentation I left in the description. We are going to use glUniform1f since we are only inputting one float, and then for the inputs we'll use the UniID and 0.5f. Now if you press run, our triangles should be bigger. As a final step, I will add some error checking in the shader class since we don't have debugging for our shaders, and so it would be nice to get a basic error message when a shader fails to compile. If you want to know how the error functions work, I left a link in the description to a Wikipedia article on them. Don't forget to add comments to everything to make sure you understand what you've written. And as always, the source code and some exercises are left down in the description. So now let's take a look at textures. Textures can be one-dimensional, two-dimensional, or three-dimensional, but in this tutorial we'll only look at the two-dimensional textures as they're the most common type of texture. So the first thing we'll want to do is to import an image into our program so that we can make it into a texture and display it. In order to do that, we're going to use this popular open source library called STB. To install it, go to your project folder, then Libraries, and then Include. Now create a folder named STB, and inside of it create a text file named stb_image.txt. Now go to the link I left in the description, press Ctrl A to select everything, and then copy paste it into the text file we've just created. Make sure to save it and then rename it to stb_image.h. Now create a CPP file named stb.cpp in your project source files and write the following into it so that we'll only use the things we need from this library. Now right click the CPP file and click on compile. Make sure to only do this once. That's it. Now if you want to use the library, simply include the header file into the file you want to use it in. I'll do that in the main.cpp file. Now, before we get to the texture, let's make sure we have the coordinates for a square so that we can better see our texture when displayed. Don't forget to also change your indices and the glDrawElements function. Run your program to make sure you do indeed get a square. If everything is alright, then let's import our image in. Keep in mind that square textures in powers of 2, such as 1024 by 1024 pixels or 2048 by 2048 pixels, are better optimized than textures with a random number of pixels, so do try to make them fit this format. I'll be using this image of Bobcat that's 512 by 512 pixels, which I'll put into a textures folder in resource files. Don't forget to also put the image in your project's main folder. First, we have to create 3 integer variables to store the width and height of the image in pixels and the number of color channels it has. Then we'll store the image itself in an unsigned character array named bytes using the function stbi_load and giving it the location and name of the image, the pointers of the variables we created, and 0. That's it for importing it in. Easy, right? Now let's create the texture object itself. Just like any OpenGL object, we'll first create a reference variable of type GLUINT and name it texture. Now just use glGenTextures to generate the texture object, giving it the number of textures you want, 1 in our case, and the pointer to the reference variable. Since we've created it, we also want to delete it at the end of the main function. We now need to assign the texture to a texture unit. You can think of texture units as slots for textures that come together as a bundle. These generally hold about 16 textures and allow the Fragment shader to work with all 16 textures at the same time. To insert our texture in the slot of a texture unit, we simply need to activate the texture unit we want using GLActivateTexture, plugging in the index of the texture unit, and then binding our texture with GLBindTexture, inserting the texture type and its reference value. Since we now have our texture binded, that means that this would be a good time to adjust its settings to our liking. First, we'll have to choose how we want our image to be processed when scaled up or down. We can choose GLNearest, which keeps all the pixels as they are. This is preferred when working with pixel art. Or we can choose GLLinear, which creates new pixels according to the pixels nearby. This generally results in a blurrier image. Which one you choose depends on your needs in a certain context. For now, I'll just go with GLNearest. I'll use the GLTextParameter function to tweak our texture settings and input the type of our texture, the setting we want to modify, and the value we want to give our setting. I'll modify both the min filter and mag filter settings. Now the second setting is how we want our texture to be repeated. We can choose between GLRepeat, GLMirroredRepeat, GLClampToEdge, and GLClampToBorder. The first one simply repeats the image. The second one repeats the image but mirrors it every time it repeats it. The third one stretches the borders of the image, and the last one simply puts a flat color of your choice outside the image. Note that you can mix and match them since they only apply on one axis. So you could have the texture repeat on the vertical axis but only have a flat color on the horizontal axis. These axes are named STR, corresponding to the common X, Y, and Z axes. Just like before, we'll use GLTextParameter plugging in the texture type, the setting we want to modify, and the value of our setting. Make sure to do this for both the S and T axes. If you want to use GLClampToBorder, you'll have to also use GLTextParameter plugging in the texture type, GLTextureBorder color, and the color of the border, which should be an array of 3 or 4 floats. Now that our settings are complete, we can generate the texture using GLTextImage2D and inputting the following: the type of texture, 0, the type of color channels we want the texture to have, the width, the height, 0, this is just the legacy leftover thing, the type of color channels our image has, the data type of our pixels, and the image data itself. The most common types of color channels are GLRGB and GLRGBA. The first one is for JPEGs and the second one is for PNGs. If you want to look at all the types of color channels and pixel data types, I left a link in the description to the OpenGL documentation. If at the end of this tutorial you get an error during compiling, then it might be because you specified the wrong type of color channels or pixel data type for reading your image. Since we've already imported the image data into the texture, we'll want to delete the data using stbi image free and also unbind the texture so we don't accidentally do something to it. The last thing you'll want to do after that is to use the GLGenerateMipMap function, plugging in the data type of the texture. This will generate the mipmaps for the texture, which are just smaller resolution versions of the same texture that are used when the texture is far away, for example. Great, we have the texture, but we did not specify how we want the texture to be mapped on the vertices. So let's do that now by adding coordinates to our vertices. The coordinates of the texture go from 1 to 0 on both axes, starting from the bottom left corner. If you would give coordinates higher than 1, then the texture will be repeated, such as in this example. Now that we've modified our vertices, we also need to add a new layout to our Vertex shader and make sure to modify our Vertex buffer object. Since the Fragment shader deals with colors, we need to export the texture coordinates to the Fragment shader and import them like so. The last thing we need to do in the fragment shader is to create a uniform of type sampler2D, call it text0, then equal the frag color to the function texture, which takes text0 and text coordinates as inputs. The uniform tells OpenGL which texture unit it should use. So in the main function, create a uniform just like in the shaders tutorial and assign the uniform the index of our slot, 0 in this case. Make sure to do this after you've activated the shader program. The last thing we need to do is to bind the texture object in the main function, and we're done. If you press run, you should see a majestic texture appear on your square. But wait, it's upside down. Well, that's because OpenGL reads images from the bottom left corner to the top right corner, while STB reads them from the top left corner to the bottom right corner. So all we have to do to fix this is to write stbi set flip vertically on load true before we load in the image file. To wrap it all up, I will create a custom texture class just like in tutorial number 4. Don't forget to add comments to everything you've written so that you can make sure you understand what's happening. The source code and some exercises to test your knowledge are in the description as always. Now let's finally leave the boring 2D plane and ascend to 3 dimensions. But first, a little correction for my past videos. In the VAO and texture class, I forgot to make the VBO and shader inputs references, so just add an and sign like so. Now for the main part. As I have mentioned before, OpenGL restricts our coordinates to normalized coordinates. So in order to bypass this and enrich our coordinates with a wider range for 3 dimensions, we can contract and expand the different coordinates using matrices. If you don't know much about matrices, then you should still be able to somewhat follow along, but I highly recommend you watch 3 Blue 1 Brown's linear algebra playlist first, as it will help you later down the line. In any case, we'll be using this nice little library called GLM for our matrices, so go to this website that's down in the description and click on download. Go to your libraries folder, then include. Now open up the zip file, go into GLM, and now extract the folder named GLM into your include folder. Once that's done, go to your project and include the following parts of the library. That's it. We can now use matrices. Easy. Alright, theory time. So in order to get a nice 3D image in perspective, we need to apply different matrices to different coordinates. Let's take a look at these types of coordinates. First, we have the local coordinates. These are the coordinates whose origin is the same as an object's origin. These are usually located at the center of an object, but that's not always the case. Then we have the world coordinates, whose origin is at the center of the world. These coordinates usually contain the location of other objects. Next, we have the view coordinates, which have the same origin as a camera or viewpoint. Notice that these do not yet account for perspective. Perspective is added in the next set of coordinates, which are the clip coordinates. These are essentially the same as the view coordinates, except they clip, aka delete, any vertices outside the normalized range, and can also account for perspective. And the final coordinates are the screen coordinates, where everything is flattened out such that it can be viewed on your screen. Now, in order to move from a coordinate system to the next, we make use of matrices. There are 3 main matrices we make use of. The model matrix, which takes local coordinates to world coordinates. The view matrix, which takes world coordinates to view coordinates. And the projection matrix, which takes view coordinates to clip coordinates. The final transformation from clip coordinates to space coordinates is done automatically. All these matrices we are applying are 4D, but we won't have to actually write them ourselves since GLM can take care of that. So let's create the model matrix. We start by creating a variable called model of type mat4 and equaling it to the identity matrix. which is simply Mat4 1.0. This is called initialization, and it must be done since otherwise the matrix is full of zeros and any transformation we would apply on it would result in the same empty matrix. Initialize the other two matrices as well. The model matrix can remain as it is since our object is in the center of the world coordinates, and that's fine for now. But right now our camera is also in the center, so we'll want to move back and also a bit up. But it's not really us doing this, but the world itself. We are essentially moving the whole world around us instead of us moving around the whole world. In any case, to do this, we are going to use the function translate, plugging in our view matrix, and the vec3, which will indicate in which direction and how much to move the whole world. Let's just move it down 0.5 and forward 2.0. Note that the z-axis is positive towards us and negative away from us. And for the projection matrix, we'll use the perspective function, plugging in the field of view in radians, the aspect ratio of our screen, and the closest and furthest point we can see. In other words, if something is closer than 0.1 units to us, then it will be clipped, and if it's further away than 100.0 units, it will again get clipped. You can see this in games when you are sometimes able to see through walls or characters while bumping into them, or when objects disappear at far away distances. Notice that I've used the function radians to transform my degrees into radians. Let's also create two variables for the width and height of our window so we can easily modify them from now on. Now all that's left to do is to import these matrices into the Vertex shader. We can of course do this by using uniforms. So let us simply declare three uniforms of type mat4 and assign them values in the main function like so. We first input their location, then 1, then GL false since we don't want OpenGL to transpose them, and finally we need to use the function valuePTR, which we give the matrix to. This is done so that we can point to the matrix object itself, not the data in it. Don't forget to have the shader activated before assigning these values. Then go back to the Vertex shader and equal GL position to the projection matrix times the view matrix times the model matrix times a vec4 whose 3D coordinates are a pos and the fourth dimension is 1. Now if you run the program, you'll notice that things look different, though you can't really see the perspective since the plane is flat and parallel to us. So let's make a pyramid. I'll start by setting the coordinates, colors, and texture coordinates, then the indices, and finally I'll modify the GLDrawElements function, which I'll generalize like so we don't have to bother with it again. I'll also use this brick texture, which you can find in the description. Now if you press run, we should see our pyramid, but sadly it just looks like a triangle. So let's make it spin so that we can see it in its 3D glory. We simply have to apply the rotation function to the model matrix, giving it the matrix we want to modify, the rotation in radians, and the axis we want to rotate it about. In this case, that would be straight up, so y equals 1. Then just create a simple timer that will change the rotation by half a degree every 60th of a second. If you press run, you should see the pyramid spinning around. But you'll also probably notice some weird glitches. That's because we're not telling OpenGL to account for the depth of these triangles, so it's unsure which triangle to put on top of which one. To fix that, we simply need to enable depth testing once, using GL enable GL depth test, and when we clear the GL color buffer bit, we should also clear the GL depth buffer bit. And now we're finally done and have a nice 3D spinning pyramid. Don't forget to add comments to everything you've written to make sure you understand it, and as always, the source code is in the description. So now let's add a camera class to make our lives easier. First, start by creating a header file named camera.h, preventing C++ from opening it twice, and including all of the following. For the camera class, we'll put everything in the public section, starting with a vec3 for the position of the camera, a vec3 for the orientation aka direction of the camera, and another vec3 for the up direction. Now we'll also want a place to store our width and height in. The last two variables will be the speed of the camera and the sensitivity of the camera when looking around. I'll also make a very simple constructor, a matrix function which will create and send the view and projection matrices to the shader, and a function to handle all the inputs. Now create a new CPP file named camera.cpp and include a camera header. For the constructor, we'll just assign values to the width, height, and position. For the matrix function, we first want to initialize our matrices, and then we'll make use of the lookAt function. The lookAt function takes the position from which you want to look at something, the target you want to look at, and the up vector. In our case, this would be the camera position plus our orientation, and the up vector. The orientation vector is always of length 1, and we'll be using it as the vector we want to look at, so to say. For the second matrix, we'll just do what we did in the last tutorial. Then we'll simply export our matrix to the Vertex shader. Good, now let's go to the main function and include the camera header. Let's delete the old stuff, including this scale uniform we had left over from a few tutorials ago, and create a camera object named camera, giving it the width and height variables and the position 002. Now in the while loop, delete the old stuff again and use the matrix function naming the uniform cam matrix. The last thing we need to do before getting back to what we had last tutorial is to go to the Vertex shader and replace all the previous uniforms with a cam matrix uniform. Now, if you press run, you should have the exact same thing we had last time, except for the spinning pyramid and the fact that everything is now much cleaner in the main function. Now, let's just add some inputs to the camera. I came up with these on my own, so they might not be the best, but they work just fine. I'll start off with the WASD controls, for which we'll simply need to add or subtract from our position the speed times the orientation or the right vector, which we get by doing a cross product between the up vector and the orientation vector. Make sure to use ifs and not else ifs, since we want to be able to modify multiple of these at the same time in order to go diagonally. Now I'll just add space for going up and control for going down and make it so that when I hold shift my speed increases and when I release it my speed goes back to normal. Now include the inputs function in the main while loop, and then if you boot up the program you'll see that you can move about. Though you can't really look around, so let's add some mouse controls. So I'll do an if and say that if I hold down the left mouse button, I want my mouse to disappear, and if I release it, I want my mouse to appear again. Now I'll create two doubles for the X and Y positions of the mouse and assign them values using the function GLFW get cursor position, plugging in the window and coordinate references. Then create two variables for the rotation of our orientation vector and make them equal the sensitivity of the mouse times one of the coordinates, but make sure to adjust both coordinates since they normally start in the top left corner, but we want them to start in the middle of the screen and be normalized, so subtract from them half the height or width and then divide them by the height or width. Now, in order to prevent the camera from being able to do a barrel roll, we want to preemptively calculate the new position of the orientation around the x-axis, and if the angle between the new orientation and the up or negative up vectors is not less or equal than 5 degrees, then we assign the new orientation to the orientation. Then we also apply the Y rotation to the orientation, which we always apply since we want to be able to spin around as much as we want. At the end of the function, we also want to set the position of the mouse to the center of the screen so that the mouse doesn't end up wandering in a corner and stopping us from freely moving the camera. Now, if you start the program, you'll notice that if we try to look around, our camera jumps. We can easily fix this by adding a new variable to the header named first click, And then in the inputs function in the mouse part, we want to check if it's the first time we pressed the left mouse button since we've looked around. If it is, then we reset the mouse position to the center and make the first click variable false. The last thing we need to do is to make the first click variable true when releasing the left mouse button. Now everything should be running smoothly. As always, the source code is in the description, and don't forget to add comments to everything to make sure you understand it. So now we'll add some lighting to our scene. First, we'll slightly modify the camera class so that we can efficiently use the cam matrix on multiple objects and make sure the new camera functions work properly in the main function. Next, we'll add a cube that will serve as our light source. Watch my previous tutorials if you don't know how to do this, especially my coordinates video if you don't know what the light pose, vector and light model matrix are for. Then, if you start up the program, you should see your main object and a small cube that's completely white. So, as you may have noticed in that nice little game called Real Life, light can have multiple colors. Usually it's white, and because of that it shows the true colors of objects, so to say. But if a light source is, let's say, red, then all objects will appear reddish. We can simulate this by multiplying the color of an object with the color of our light, both of which are in RGB. For example, if our light has the RGB values of 100, then when it's multiplied with the color of the object, the green and blue parts will become 0, while the red part will stay the same since it's multiplied by 1. This simulates what happens in real life, as only the red color is reflected back to us, even though the object is actually orange. So let's make a vec4 called light color and make it completely white. Then we'll want to export it to both the light fragment shader and the fragment shader of our object. In the light one, we'll simply use it as the color of the object, while in the object shader, we'll multiply it by whatever you currently have in your frag color. We are now able to simulate the color of the light hitting the object. So next, we'll want to simulate the intensity of that light. You've probably noticed that the higher the angle between a surface and the source of light is, the less intense color is on that surface. This is best seen on a sphere, where you can clearly see the gradient of the intensity along the curve of the sphere. In order to get this angle and calculate the intensity, we'll need the position of the light, which we already have, and the way to know the slope of the surface. The traditional way of doing this is to represent the slope of the surface by a normal vector. So far we've had coordinates, colors, and texture coordinates inside the vertex. Now we'll also want to add normals. Normals are unit vectors, aka vectors of length 1, that help us calculate how light should act on a certain object. This can be either perpendicular to the surface of one triangle, called face normals, or arranged in a different way, such as being perpendicular to the plane created by all the adjacent vertices, for example, called vertex normals. If you go for the first option, you will get what's called flat shading, where all your triangles are clearly visible. If you go for the second option, things look a lot smoother and nicer. But which one you choose depends on your mesh and on your artistic style. Since we have a pyramid, we'll go with the flat shading, since the smooth shading looks weird on very angular geometric shapes such as cubes or pyramids. Now, since the normals will be different on each side of the pyramid, we won't be able to fit all of them in just 5 vertices like we have here. We'll have to duplicate some vertices in order to change their normals. So I'll just do that, plugging in my pre-calculated normals for each face. Don't worry if some of your normals are not unit length, it does not matter since we can just normalize them in the shader later. Don't forget to also change your indices, the GLDrawElements function in case you haven't automated it like me, and add a new attribute to the VAO. So now for the vertex shader, we'll include the normal layout and also export it to the fragment shader, along with the current position, which we'll use to calculate the direction of light. For consistency purposes, I'll also import the model matrix for the pyramid. Now in the fragment shader, we import the normal and current position and the light position uniform. Then in the main function, first normalize the normal vector, and then get the light direction vector by simply subtracting the current position from the light position and normalizing it. We now have the two vectors we need. The lighting we're implementing now is called diffuse lighting, so I will create a float called diffuse. Then in order to make it such that the larger the angle between the two previously calculated vectors, the less intensity the light has, we can simply use a dot product between them, which is equal to the cosine of the angle between them since they are normalized. Now this can also be negative, and since we don't want negative colors, we'll take the maximum value between this and 0. All that's left to do is to multiply the diffuse float with the color of the object, a texture in our case. If you now boot up the program, you will notice that we have some nice lighting, but that the areas not touched by light are extremely dark. This is realistic in our case, where we only have one object and are in a vacuum, but generally speaking, it's not realistic, as light will bounce from other objects that are around onto our object. This bouncing is expensive to calculate and pretty advanced, so for now we'll simulate it by simply giving a base value of brightness. This type of lighting is called ambient lighting. So just create a float called ambient and give it a value like 0.2 and then add it to the diffuse value in the frag color. Boot up again and notice this looks a bit better. The last type of lighting we have to add in order to complete our lighting algorithm, which by the way is called Phong shading, is the specular light. This is dependent on the angle you look at an object from, so you'll need to import the camera position into the fragment shader first. Now create a float specular light, which will represent the maximum intensity of this type of light. Now we need a view direction, which should just be the cam position minus the current position normalized. And the other thing we need is the direction of the reflection, which we can get by using the reflect function, plugging in the negative direction of the lighting, since we want the vector to be towards the plane, not away from it, and the normal. Then create a float, spec amount, which will store how much specular light we have at a certain angle with our camera. So the larger the angle between the view direction and reflect direction is, the weaker we want the specular light to be. So just use a dot product like before and take the max between this and 0. Then we'll want to raise this to a power. The higher the power is, the more point-like and defined the specular light will be. I will go for a lower power such as 8. Now create a float named specular and multiply the specular light with the spec amount. Last thing to do is to add the specular float to the diffuse and ambient floats. Now you have some nice decent lighting for your scene. Don't forget to add comments to everything you've written to make sure you understand it, and as always, the source code is in the description. Today, I'll show you how to improve specular lighting with the use of specular maps. I'll start by slightly modifying the texture class so that it's easier for us to assign multiple textures to the same shader. Then, I'll delete the pyramid we had and simply create a flat plane. I'll also import this wood texture and the specular map. You can find this in the description. I'll also assign the wood texture to the plane. Now, as you can see, the specular light is just sort of flat. Areas that shouldn't reflect much light, such as the cracks in the wood, still somewhat do so. And the areas that should reflect a lot of light, such as the smooth tops of the wood, don't really do so. In order to fix this, we can make use of something called a specular map. These types of maps are black and white textures that tell the program where specular light should appear and how strong it should be at that point. The whiter a pixel on the specular map is, the more specular light you'll get, and the blacker a pixel is, the less specular light you'll get. The idea is really simple. So to implement it, we must first import the specular map into our program. Make sure to import it using GLRed, not GLRGBA, since it only has one color channel, not 4. Then simply export it to the shader and bind it in the main function. Now import the texture in the shader and in frag color multiply its red value by the specular light and add that to the other texture, which is only multiplied by the diffuse and ambient lighting now. That's it for the specular light. Now I'll just change the value to make the light look better on the wood, and if you then boot up the program, you should see that the specular light looks much better and it makes the whole texture look better overall. As always, the source code is in the description. Now let's take a look at different types of light. There are 3 main types of light: point, directional, and spotlight. Point lights illuminate the environment in all directions, but the intensity of their light withers as it gets further away. This is the type of light we've used till now, except we didn't incorporate the loss of intensity. So let's quickly do that. First, let's create a vector function named pointLight and copy-paste into it all the things from the main function and make fragColor equal the output of this function. So the intensity of light has an inverse square relationship to distance in real life, but in computer graphics we use a somewhat more complicated equation to better control the properties of the light. Instead of having 1 over distance squared, we have 1 over a quadratic equation with respect to distance. This quadratic equation has 2 constants, a, the quadratic term, and b, the linear term. We can modify these to change how fast the intensity dies out and how far the light reaches. There is no general perfect number for these constants, you just have to play with them and see what works for your scene. Just know that usually the numbers are smaller than 1 if you want your light to reach somewhat far. So to implement this, we first need a distance to the light. The distance is simply the length of the vector that comes from subtracting current position from light position. Since we already used this in our diffuse lighting, I'll create a variable named lightVector so that we don't have to calculate it twice. Now we can get the distance by simply using the length function. Lastly, we just write out the equation with the variables and apply it to the specular and diffuse lighting. Here are some examples of the results I got using different constants. The second type of light is the directional light. This is usually considered to be so distant from your scene that the light rays it emits are essentially parallel to one another, just like the rays of the sun. This has no dimming and is actually the easiest of the 3 to implement. We just need to copy-paste part of the code from the point light, and instead of calculating the light direction based on some positions, we simply give it a constant light direction as a normalized vector 3. Just note that it should point in the opposite direction you want it to affect due to the way I wrote the code here. So if you want the light to come from above, it should point up, not down. And if you press run, you'll see everything is lit up as it should be. The last type of light is the spotlight. The spotlight only lights a conic area just like a flashlight or a desk lamp. For this, we'll copy-paste the point light code again and begin by adding 2 floats which will represent the cosine values of 2 angles. The first angle is the angle between the inner cone and the direction of the light, and the second angle is the angle between the outer cone and the direction of the light. We make use of these 2 cones in order to have a nice gradient between darkness and light areas, since if we only made the use of 1 cone, we would just have a direct cutoff from light to darkness. I wrote a cosine value directly in order to save computational power. Do not write the inner and outer cones in terms of angles, since that will require extra calculations and it will slow down the program. Now we need to calculate the angle between the current part that is being lit and the central direction of the light using a dot product. This will give us a cosine value which is perfect to compare with our own cosine values. The last step is to get the intensity at the current spot, which is done using this formula. Make sure to also clamp it between 0 and 1 so you don't get weird values. And lastly, just multiply the diffuse and the specular lighting by the intensity variable. Start the program and you'll see that the light is restricted to one area. Don't forget to write comments for everything you've written to make sure you understand it, and as always, the source code is in the description. In this tutorial, we'll wrap up all the classes we've made till now and a big part of the code in the main function into a mesh class that will also serve as a stepping stone for importing models in a future tutorial. First, a rough definition of a mesh. A mesh is a dataset that almost always contains vertices, often contains indices, and sometimes contains textures as well. And they are generally used to create 3D models. So let's create a header file for the class. First, we'll want to include a string library, and then the VAO, EBO, camera, and texture classes, since we want the three of our classes dependencies to look like this. Now for the class itself, I'll declare 3 vectors named vertices, indices, and textures. Note that these are C++ vectors and not GLM vectors. We are using vectors instead of arrays since we can't know the size of our arrays, so it's best to keep things flexible in terms of storage. As you can see, we get some errors, but don't worry, we'll fix those after we finish writing everything in here. Next, we also want to store our VAO since we'll be initializing it using this class. Then, for the constructor, we'll simply input the vertices, indices, and textures. And lastly, we'll make a function draw that will take in a shader and a camera. Now for the errors, let's go to the VBO class. If you've been paying attention, you probably would have noticed that our vertices vector contains a structure named Vertex. But we don't have one so far, so let's create one right here. I'll simply name the structure Vertex and give it 3 vec3s for the position, normal, and color, and then a vec2 for the texture coordinates. Having our data packed in such a structure is nicer than simply having all the data in one array, at least in my opinion. Don't forget to also include the GLM library though. Now we need to patch up the VBO class constructor to accept a vector of vertex structs instead of an array. So let's also include the C++ vector, and since we're using vectors instead of arrays, we can now also get rid of the size input since we can calculate that inside the class. So in the VBO.cpp file, we can replace the size by vertices.size times size of vertex, and for the data, we just write vertices.data. If you return to the mesh class, you should have no more errors. Now let's do what we did for the VBO class to the EBO class as well, replacing the array with a vector. Now for the main part, let's create a mesh.cpp file and start writing the functions for this class. Let's start with a constructor by simply assigning the inputs to the variables of the class. Then copy-paste the initialization of the VAO from the main function and modify the variables names slightly and also the way the attributes are stored. We want the position first, then the normals, then the colors, and finally the texture coordinates. Since we've modified this, we should go to the vertex shader and rearrange the new order of the vertices sections properly, and then do the same thing in the fragment shader as well. It's not mandatory to keep them in this specific order when importing or exporting them, but it just looks nicer to have them in the same order everywhere. Though it is important to have them in the proper order when choosing the layouts in the vertex shader. Now let's continue with our mesh class by writing the draw function. We'll start by activating the shader and binding the VAO as usual. Now we'll have to do something a bit more complicated in order to properly load the textures, since we won't always know how many textures a mesh has. So let's create 2 unsigned integers that are equal to 0 and are named numDiffuse and numSpecular. These will keep count of our 2 types of textures. Then we'll want to go through all the textures where we'll have a temporary string called num and another temporary string called type, which will store the type of the current texture. The problem is that our textures don't store their type yet. I mean, they do, it's just that they store a different kind of type. In any case, we'll want to modify our texture class by changing the type variable to a constant character array and so also the type of the input in the constructor. Then in the texture.cpp file, we'll want to make all the text type equal GL texture 2D, since 99% of the time, that's what we'll be using. Now let's go back to our mesh.cpp file and create some checks. We'll check if the type is diffuse, and if it is, make the num equal to a string of num diffuse and then increment it by 1. Then we'll do the same check for specular and increment num specular. Now we want to take care of the uniform using our function textUnit, plugging in the shader, then a C-string composed of our type plus num and the unit of our texture. Then simply bind the texture. So our uniforms will be named diffuse 0, diffuse 1, diffuse 2, specular 0, etc. So in our fragment shader, we want to replace our text 0 uniform by diffuse 0 and our text 1 uniform by specular 0. Then again, go back to the mesh.cpp file and send our cam position and cam matrix uniforms and also write the GLDrawElements function. All that's left to do now is to modify our main.cpp file. First, we can delete all the includes and only include our mesh class. Then we'll have to modify the vertices array, and after that, in the main function, make an array for our textures as well. Delete the VAO initialization and create vectors for our vertices, indices, and textures using the arrays from before. Then create a mesh named floor with the vectors we've just created. Do the same for the light, except we don't have any textures on the light, so we'll just place the same textures as a placeholder. In the while loop, we can just delete all the drawing stuff for the light and floor and replace them with our draw function. And finally, we just need to get rid of some of the deletes at the end of the file. If you press run, everything should now be fine. If you have any errors, go over the video again or check out the source code in the description. As always, you should add comments to everything you've added to make sure you understand what's happening. In this tutorial, I'll show you how to import 3D models into your OpenGL application by building a very basic importer. This tutorial will also be longer than usual and only have visible results at the end, so please have patience and pay attention to what I'm doing, otherwise you might end up with a chain of errors by the end. A small note first. As you may know, when it comes to storing images, the industry is pretty standardized with the use of PNGs and JPEGs. But when it comes to 3D models, there are dozens upon dozens of file formats, many of which are proprietary. This diversity of file formats makes it a lot more difficult to export and import models from one program to another. In the spirit of standardization, I will use the GLTF file format for this tutorial as it is made by the same people who've made OpenGL, the Kronos group, and it seems to be a promising file format that could become the standard in the future. I left a link to a nice article on this by the developers of the Godot engine in the description. Now for the actual tutorial. GLTF makes use of the JSON file structure, so the first thing we'll need to do is to install Niels Lohmann's JSON library from GitHub to be able to parse JSON files. That does it for the libraries. Now we can create a header file for our model class, a model being a group of meshes. Then we'll make a constructor that will take in the name of a file and a draw function that will take in a shader and a camera. In the private section, we'll want to store the name of our file, a vector of bytes with all the data of the model, and a JSON object, which I'll explain more about in a moment. Now for the model.cpp file, let's read the GLTF file in the constructor using the same function we used to read the shaders. Then we parse the text and store it in the JSON variable. So JSON files work like dictionaries within dictionaries. Dictionaries have keys and values associated to those keys. If you give a dictionary a key, it will point you to a certain value. This JSON object abstracts the GLTF file into such structures. So let's just store our file and then equate our data variable to a function getData. We want this function to get us a vector of bytes from an external binary data file. So let's create a string named bytes_text to hold the raw text. To get the location of the file, we can look at the buffer's key, which will point us to an array where we want to look at the first element, which will again be a dictionary, so we again want to use a key. This time the URI key. This URI gives us the name of a .bin file which contains the binary data. Then we just get the text, put it in a vector and return it. So now that you have your first taste of the JSON file, let's take a closer look at it. The file has dictionaries which contain arrays of other dictionaries, thus making it a sort of tree. But it's not a very nice tree, since many branches will contain indices that will point us to other branches, so things will get entangled pretty quickly. In order to avoid confusion in such a situation, I like to start from the leaves and work my way down to the root of the tree. Keep in mind that I will be taking some shortcuts in the GLTF file, since otherwise this importer would become too complicated. With that out of the way, here is a simplified view of one of the main branches of the tree and the one we care most about. At the top, we have our data that's stored in the buffers. But to know which parts of it we should read, we need to take a look at the buffer views. Then again, these will only tell us where to look, not what to look for. In order to know what types of data types we are reading, we need to look at the accessors. So great, the accessors tell us that we are reading an int or maybe a vec3, for example. The problem is that they don't tell us what these are used for. A vec3 could be both a position and a normal. To find out which is which, we need to once again take a step back. It's just that this time we'll have to split in two. If we look at the attributes, then we know which accessors are part of which vertex attributes, aka positions, normals, texture coordinates, etc. If we look at the primitives, we can find the accessor of the indices of our mesh. Keep in mind that the attributes are pointed to by the primitives. These also point to materials, which point to textures, but we'll ignore that since materials often have PBR data, and since we haven't learned about that yet, we'll skip directly to the textures, ignoring the materials. If we get back to our main branch, the primitives are pointed to by the meshes, which are again pointed to by the nodes, and lastly, the scenes. In our case, we'll have one scene 99% of the time, so we can ignore those and just focus on the nodes, which will contain pointers to all our meshes. Don't worry if you don't fully understand what I just went through. It's normal to not fully comprehend it from the start. You should get a better idea of it when we write the code. So let's start with the leaves by assuming we get an accessor node. Let's declare a getFloats function and a getIndices function. Then we'll also want to declare three functions that will take the array vectors outputted by the get functions and group them into GLM vectors. So we'll first want the buffer view, the count, the byte offset, and the type from the accessor. Notice how I used the value function instead of brackets to get the byte offset and buffer view. The brackets will simply give you the value of the key, while the value function will give you the value of the key if it exists. Otherwise, it will give you the second input. These two parameters are not always found in GLTF files, so I want the backup value for them in case they do not exist, while the other two always exist, so I don't need any backup. To see which of these are always found and which are not, check out the specification of GLTF on GitHub, link in the description. Now, using the index of the buffer view we got, we want to create a JSON variable for the buffer view dictionary from which we'll get the byte offset. Now, to explain all the parameters we got. The buffer view index simply pointed us to the correct buffer view as mentioned a second ago. The count tells us how many floats we have to get. The accessor byte offset tells us from what index to look at the data with respect to the beginning of the buffer view, and the byte offset tells us where that buffer view starts. The reason we have two different offsets is that sometimes two different accessors may share the same buffer view. For example, we could have a vec3 buffer view, which is shared by a positions accessor and a normals accessor. And finally, the type tells us how we should group the floats. It can either be scalar, vec2, vec3, or vec4. Using this type, we'll want to get the number of floats per vertex. Then, in a for loop, go over all the data. We'll store the bytes in a temporary array, which we'll then use in the function memcpy to transform the bytes into a float, which we'll then store in the variable value and push it in the float vec vector. At the end, simply return the float vec. Now I'll do the same thing for indices, except this time we won't check the num per vert, since indices are not stored in vertices. Instead, we'll check the data type of the index itself, and according to that, read it differently from the data. The index can either have type 5125, which is an unsigned integer, type 5123, which is an unsigned short, or type 5122, which is a short. Now for the grouping functions, we'll simply go over all the floats in the float vector and group them in their corresponding GLM vectors. Really easy stuff. Using the getFloats function, we'll be able to get all the attributes of a vertex, so the next logical step would be to combine those attributes in a vertex. So let's declare a function for that, which takes the vertices, normals, and texture coordinates and combines them into a vertex, which will be put in a C++ vector. Very straightforward stuff. Notice that I did not include the colors in here, since even though we declared them in our vertex, they are actually very uncommon in 3D models, so we can ignore them. We now have the vertices and indices. All that's left for a complete mesh is the textures. But before we take care of those, we should first modify our texture class a bit. First, we should remove the last two inputs of the constructor, since we'll atomize the first one and the second one is the same 99% of the time. For the first one, we'll simply check the number of color channels a texture has and assign a corresponding color type to the texture. Then for the second one, we just replace it everywhere with GL unsigned byte. So now let's create a getTextures function. We want to skip directly to the images key, which will give us an array of URIs. Here we loop over all of them while keeping track of the unit of each texture. Then, if the texture contains base color in its name, it's a diffuse texture. If the name contains metallic roughness, we can somewhat use this texture as a specular map. Keep in mind that this way of checking the type of a texture is not ideal and may differ from model to model. Also, the reason the metallic roughness just sort of works for a specular map is because it's something that's meant for PBR. The problem with this function, though, is that it can load the same texture multiple times, which we don't want to do since it will use up a lot of RAM. To prevent that, we want to create two variables, loaded text name and loaded text. We'll use loaded text name to determine whether or not we've loaded a texture, and loaded text to store the textures for all meshes to use. Then in the function, we'll add a skip variable, which will become true if the texture we are currently trying to load has the same name as a texture in loaded text name. If it becomes true, we don't load it anymore, instead simply pushing an already loaded texture to the textures vector. We can also replace the unit by the size of the loaded text vector as well. This does it for our textures. We now have all the elements needed for a mesh, so let's make a loadMesh function that will take in as an argument the index of a mesh we want to load. We'll also want to create a meshes vector to store all the loaded meshes into. So first, we want to get the indices of all the accessors of the vertices. Then we'll simply use our getFloats and groupFloats functions for the attributes of the vertices. After that, we assemble our vertices and get our indices and textures. Then we just create a mesh with these three vectors and push it to the meshes vector. Now we can load multiple meshes by simply iterating over them. The problem is that we don't know where to place those meshes, so they will likely all be within one another at the origin. In order to know where to place them and how big they should be, we must extract the matrix transformations from the GLTF file. And we can't just get the matrix of each mesh, but must instead keep track of what children each mesh has in order to multiply the matrices of each mesh together. All the information for the matrices and the relationship between meshes is in the nodes. So let's create a function named traverseNode, which takes the index of a node and the matrix, making it have the identity matrix as a default value. Then let's also create vectors for different types of transformation matrices. We have translations which move the mesh, rotations which rotate it, scales which change its size, and matrices which are a combination of the aforementioned, but we can't know if the first three will be used or just a matrix, so we need to account for both. We must first modify our mesh class by adding these transformations to the draw function as inputs with default values that don't change anything, and then sending them to the shader at the end of the function. Don't forget to also create uniforms for these transformations in the vertex shader and multiply them like so. I put a negative sign in front of the rotation matrix since that's what I found to work. It might be a bug in my code or the fact that GLM and GLTF use different rotation standards, aka clockwise versus counterclockwise. And since we're in the vertex shader, we also need to rotate the texture coordinates by 90 degrees, which we can do with this matrix. This again either has something to do with a bug in the code or different standards. What's important is that it works decently well. Now for the function itself, we'll want to get a current node as a JSON object and then extract the transformations if they exist. Notice how for the rotation quaternion, I get the indices in the order 3012 instead of 0123. This is because GLTF encodes quaternions as XYZW, while GLM uses them as WXYZ. Again, just standardization problems. Now we want to combine all of these transformations, including the matrix we get as an input. Then we check if we have an index to a mesh, and if we do, we push all the transformations and load the mesh. After that, we check if the mesh has any children, and if it does, we want to apply this same function to all of them, while also giving them the current matrix we have. So this function is recursive, and so we'll split along the paths of the tree till it gets to all the nodes. Now we can write this function in the constructor and give it 0 as an input. The last thing we need to do is write our draw function, and that's it for the model class. In the main.cpp file, we just have to include the model class and delete all the old mesh related stuff. Then get some models, create a model object, and draw it in the main while loop. Here are some examples of models I've been able to load in. I've left some models that should 100% work in the repository of this tutorial on GitHub. So if you're getting some errors, check those models to see if you have a problem with your code or the model you're trying to load in. Again, keep in mind that this importer is in no way complete and is in fact very basic, so don't expect to be able to load in any model you find on the internet. I find that a decent amount of models from sketchfab.com work pretty well, especially if they don't have too many meshes. That's it for this tutorial. It was a really long one, but also a very rewarding one if you ask me. As always, don't forget to add comments to everything you wrote to make sure you understand it, and the source code is in the description. Bye!